The Stanford Torus is a vast space habitat design intended to allow thousands to dwell safely and comfortably in space. But how do we build such a structure? Today we'll be looking at the Stanford Torus Space Habitat, one of the best-known designs for a spin-gravity space station designed as a long-term dwelling for an entire community of humans and a true ecology. An enormous donut, often a mile wide in designs, this wheel shape can be combined with other wheels of the same size or not, around a central axis with minimal artificial gravity, while those inside the hoop benefit from full gravity caused by rotation of the hoop. The spinning wheel design, in its most well-known incarnation, would have a diameter of 1,790 meters, or 1.11 miles, mass at least 10 megatons, mostly in radiation shielding, and house an estimated 10,000 people at an estimated 67 square meters or 721 square feet per person. Bigger designs are possible, as are smaller ones, as this radius, 895 meters or 2,936 feet, was selected for it and other designs, as is the radius that spinning object can have while rotating exactly once per minute, 1 RPM, and producing the 9.8 meters per second that we call normal gravity. Today we'll be both looking at the basics for folks who don't know it, and deep diving some aspects for the folks who are already quite familiar with it. So no prior knowledge is needed, but it doesn't hurt either. While not the first design by any means, the Stanford Torus was an in-depth design with serious analysis and emerged in 1975. Roughly at the same time Gerard K. O'Neill's Island 1, 2, and 3 designs, the latter being the O'Neill cylinder we so often mention on the show. Both approaches are immense and designed for many thousands to even hundreds of thousands of people. Back in 1975, NASA conducted a summer study at Stanford University and released some findings. After concluding humans needed pseudogravity or spin gravity to live, and bringing up the von Braun wheel design, and Arthur C. Clarke's examples in sci-fi, like the giant spinning cylinder ship in his 1973 novel, Rendezvous with Rama, they present 4 principal shapes for discussion. The first is a sphere, hollow and spinning like a planet does, only you live on the inside and centrifugal force holds you down. This is basically the Bernoulli sphere, which will give its own deep dive in a couple months. The second is a cylinder rotating on its long axis, and is generally the other preferred design, namely the Island 3 O'Neill cylinder, which we've done a few videos on but may update next year. The fourth is where we take a dumbbell and spin it around, what we often call a hammer hab or a bolo hab, and this will get an episode in early spring 2025, as it is in some ways the easiest approach, especially when you're just trying to give gravity to a small crew for a long trip. Number 3 is the Torus design, which is a ring habitat that has a circular tube, the donut, rather than simply a flat ribbon, since walls and ceilings are a good idea. This is obviously the main focus for today, and all 4 approaches got a detailed look in that study, but the Torus design inherited the name of the study, and the study did conclude that while the Torus was not the best design in many respects, it seemed to give the best desirable balance of qualities they were reviewing. I generally tend to favor Type 4, the hammer habitat for interplanetary ships, and the cylinder for bulk habitation. The sphere tends to be a bit of a holdover, as Bernoulli proposed it way back near the beginning of the century and it latched onto people's consciousness. It does have some pros, but its big con is that it's a spinning sphere and has no gravity at the poles and full gravity only at the equator. This can be useful sometimes. You might like your docking ports at those zero-G poles and your residential quarters for people down at the equator. A cone-shaped habitat also has this varying gravity, as would a hemisphere, like an orange sliced in half, that had a big window to let light in through that flat slice section, which might be an option for asteroid mines or cheap farm habitats. Similarly, while we envision the Stanford Torus as a torus or hoop or donut, that toroid could be a hexagon instead of a circle for its cross-section. This might be more structurally sound, and you end up having that on the outside or bottom edge anyway for flooring, since nobody wants to walk on a curved floor, especially as the gravity won't point at the floor but at an angle. One area the torus beats the cylinder in very handily is the amount of air needed inside one, as the hoop has a roof, whereas the cylinder goes all the way to the other side and needs to be filled with air for its entirety. Now, for a lot of folks, spin gravity is a well-known concept. We've discussed it in many episodes, particularly our Megastructures playlist, so we'll keep it concise for today, but here's the basics. First, if you ever had someone tell you that centrifugal force is not real, while that statement is not exactly wrong, it is usually being said by folks who terribly misunderstood the concept. What qualifies as a real force is very debatable, but saying centrifugal force isn't real because it's actually the wall or floor shoving back on you as you accelerate around a curve is not really any more useful than saying electromagnetic force is not real because it's transmitted by virtual photons, not real ones. You can ask your laundry how real centrifugal force is when it emerges from your washer without water dripping from it. What we usually call the four fundamental forces these days started with gravity, electric, and magnetic fields, and those were something we found could pull or push on stuff without touching it. We realized later that electric and magnetic fields were two aspects of the same force, electromagnetism, and found there was another pair of forces at work at the subatomic scale, the strong and weak nuclear force. And indeed, the weak nuclear force combines with electric and magnetic forces into what we call the electroweak force. There's also a lot of debate on if gravity is real or a pseudo-force here. Under general relativity, it is indistinguishable from acceleration. And in reality, this is misleading because we do not mean actual versus fake. It's just the names that got slapped on these things as we discovered them and tried to classify them for simplicity of discussion. This is a regular problem in science. We find something new and have to name and classify it to usefully discuss it, but by definition don't yet understand it. So the names in taxonomy tend to later turn out to be poor choices, and physics and astronomy are full of them. Mundane forces are things touching each other and shoving. If you push or pull on a doorknob, this is essentially the electromagnetic force in action. It's not a fake force, and neither is centripetal or centrifugal force. And I am glad to say folks have mostly stopped repeating the centrifugal force doesn't exist truism. It was rampant when the show first started 10 years back, and inevitably made folks wonder if spin gravity would work. If you want an example of it working, look at the space station, and gravity is just a few percent lower there, or on any of our other manned craft besides the Apollo missions. Those folks were all weightless because they were spinning around the planet, orbiting, and their centrifugal force equaled their gravitational force, producing a zero or microgravity environment. But you can test this by moving to different places between our equator and poles and seeing how weight shifts. It's a small but very real amount, as Earth's spin at the equator produced the highest centrifugal force, counteracting gravity, while the amount at the poles is zero. The equation for this is pretty straightforward, and I'll give it to you in two formats, though in both cases as the acceleration rather than the force. Force is mass times acceleration. Your weight is a force. But except for discussing the stress on the station from being under spin, we only care about the acceleration rate and getting it to 9.8 meters or 32 feet per second, what we call 1g, 1 regular Earth gravity. That acceleration can be written as equaling the square velocity divided by the radius of your spin. That velocity, also called your tangential velocity, is how fast you're moving out of that radius and what you spin off at if you let go of the floor or rope or whatever you're attached to keep you spinning. For the Stanford Torus, that's about 94 meters per second or 209 miles per hour. Pretty fast, and a good way to give ships departing a little kick free of your station so they turn their drives on so they're further away. If you're docking on a station this way from a ship that keeps gravity by constant acceleration, like ships in the Expanse do, rather than by rotation, you dock with your ship prow, front, or nose to the outside edge of the ring and crawl up through that into the edge of that ring, which is the floor of the habitat. So we calculate that by, again, setting our desired g's on the left and the square of that tangential velocity divided by the radius on the right. We can alternatively do this by instead having the angular velocity squared on the right, then multiplying it by the radius rather than dividing. Your angular velocity isn't a speed in meters or feet or miles per second or hour or whatever. Instead, it's how long you take to complete a rotation. Rotation per minute, or RPM, are an example, and a big wheel at 1 RPM is rotating as fast as a smaller wheel at a tenth its diameter, but it is also spinning a tangential speed at its edge 10 times higher. We also often calculate size for stations at 2 RPM, because that lets us make a smaller station with the same gravity, 1/4 as wide, as the angular velocity squared, being twice as high, is 4, and thus a radius 1/4 as wide will give us the same acceleration at 2 RPM as one at 1 RPM would. We tend to hesitate to go faster than that for fear of nausea. We can probably do 6 RPM, but we are not sure everyone could, or that every organism we want to bring along could. We are pretty confident it's not lower than 2 RPM. The faster we spin it, the more Coriolis force people endure, and for starters, it would cause nausea and other discomforting effects in many people. The wider your station, and the slower your rotation, the less these problems are, but until we build some prototypes, it will be hard to know how humans and other organisms handle higher rotational rates. Bigger is better, but you will tend to build your rotating space habitat not wider than you have to. That 1 RPM structure is under constant strain, and exactly equal to what a suspension bridge on Earth would have if it were as long as that station's circumference is. So a long bridge on Earth looped into a circle, make it 1/4 as wide, and that station can be a lot thinner or sturdier, and presumably cheaper. You can add more living space by adding more length down the axis, a longer cylinder for cylinder habitats, or an extra wheel for a wheel-on-axle setup. One caveat on that though, space is nasty. It's virtually empty, and the only reason it isn't totally empty is because it's full of dangerous radiation and hypervelocity rocks that might be as small as bullets, yet carry the force to tear through a tank's armor. As a result, you need a lot of shielding, and for that summer study in 1975, the Stanford Torus has 150,000 tons of structural mass holding it together, another 44,000 tons of air, and a whopping 9,900,000 tons of shielding. That doesn't include any people or equipment, just the raw station and air to breathe, and is 10.1 megatons, 98% of which is shielding, and just over 1% of which is structure. And this is the one that's a mile wide already and designed by those engineers using known materials of the time. In this case, aluminum. Strong and lightweight materials, in terms of tensile strength, are your preferred structural materials for rotating habitats, same as for suspension bridges. But if you need that much shielding, you might build out of something cheaper or that's shielded better. That shielding is critical to the space habitat concept though, because mass is never your friend in space, and thus a space habitat with lawns and gardens and lakes always seems like a crazy idea until you remember that shielding issue. Plus, while all space habitats are by definition spaceships, we usually don't plan to move them much once we get them built and into their orbit. So instead of using lead, or whatever material works best against radiation, gram for gram, you might use soil and water. The calculation used throughout the 1975 study assumes 4.5 tons of shielding per square meter, or 0.42 tons per square foot, a bit over 400 pounds. Just taking that as is, that would represent 4.5 meters or 15 feet of water in terms of mass, and more like 3 meters or 10 feet of soil, depending on the type of soil and wetness. For my part, I think you would do more, but I'm not sure you'd use actual soil for that in favor of just using regolith, with a thinner layer of soil above. This is also why we don't think of such stations as fragile. It takes a lot to punch through a hull that's made of meter-thick aluminum or steel, and even more to then carry yourself through whatever dirt and water they have on top of that. That's a key point we don't tend to bring up much in discussing rotating habitats, and while we've mentioned it in passing, I never really thought much of it till I was chatting with a couple of the National Space Society members at our conference. A lot of folks involved in that 1975 summer study are members of the NSS, or were, it's been 50 years now, and a lot of them were founding members of either the NSS or one of the two precursor societies that merged in the mid-80s to make the NSS, the L5 Society, which was focused on building one of these habitats, and von Braun's National Space Institute. Unsurprisingly, we have multiple student contests that focus on space settlement design. One of the neat things about being the president of the NSS is that a lot of those old white papers read a lot differently when you sat over drinks or dinner or Zooms with the original authors or their students who kept it up. I also really enjoy talking to the hundreds of students who make it to the finals and show off their design in person at the contest. I'm not sure if I've had occasion to pitch joining our society before. I think I usually just mention this or that event or forum or contest we have going on, but I would definitely pitch that as a good reason to join or attend. If space development is something you are really passionate about, with the possible exception of your fellow audience members on this show, you're not going to find another group so large and devoted to the topic. So, how big is one of these habitats? Well, as mentioned, the radius can change, and so can the other radius. This can get a bit confusing since people don't always use the same names or spots for those two. Sometimes the major radius and minor radius get used, sometimes the inner and outer radius, and either can be used. Typically, the major radius will measure from the center of the donut hole to the middle of the actual donut, and the minor radius is the radius of that donut, from the middle of the tube if you're imagining walking down it. The other approach is to measure the inner radius, from the center of the donut hole to its inner edge, where the donut starts, and the outer radius measures from the center to the outside edge of the donut. Any of these can be used to calculate each other. Your major radius is halfway in between inner and outer radius, and the minor radius would be the distance from the major radius endpoint to either the inner or outer radius edge. For those watching the video, there's graphs up to look at. For all our folks listening to our various audio-only podcasts, if that wasn't clear, just Google torus and major, minor, inner, or outer radius for some visuals. For most torus designs, we assume the major radius is a good deal bigger than the minor radius, but usually not by much more than an order of magnitude. And the original design, the minor radius is 65 meters, and the major radius 830 meters. Add those two together and you get 895 meters, or the outer radius we were using for gravity calculation. Of course, that's only 1 g out of the outer radius. At the major radius is still turning 1 RPM, so gravity drops to 92.8% normal gravity. And at the top of the donut, the part closer to the center or the inner radius, it's down to 85%. You might want to be using a rotational rate that keeps the center of the hoop at the major radius at 1 g, one rotation every 62 seconds instead of 60. It depends on if you have people there or it's open air. This could be a single level too, as we often see in the artwork. Folks live down on the bottom of a bowl with terraces up the sides and glass overhead, or you might have many layers. If we assume it was all layers 3 meters high or 10 feet, then your torus's habitat cross-section is going to have 43 levels, though some are fairly narrow. A single level is a lot less, as is the tiered river valley look, though it does decently better. That is a lot smaller than its O'Neill cylinder or Bornosphere kin of the same radius, as again it is a skinny donut, and that is its main weakness. It's really built around the idea that you need a certain radius to make habitation comfortable, and that building out to that radius is your minimum constraint. At that point, you're just building a circular tube wide enough to accommodate the people you need. So it's a design for few people, not for maximum population per cost. For the original designs, the specified habitat was to be big enough to house 10,000 people. The cylinder and sphere version both massively exceeded that population because they were trying for the 1 RPM rotational rate and thus had a huge radius still and much more living area. As mentioned, we have a big contest every year with tens of thousands of students entering worldwide, and the finalist teams get to present them at our annual International Space Development Conference. Walking around to see those posters is one of my favorite parts of the ISDC. The majority of the designs are either variations of the Stanford Torus or the O'Neill cylinder, with good reason. They are basically your core designs. I remember one of the student designs had a hoop 12 kilometers in radius. Given that one of the students on that team was probably only 12 themselves, I wasn't going to criticize it, but there's really not much point to building that wide in major radius while sticking to a torus design. It makes sense for the Banks orbital or ring world because both are trying to take advantage of the actual sun in their lighting. The ring world is built to wrap a star entirely and at its Goldilocks zone distance, while the Banks orbital is that wide to have a rotational rate of exactly 1 day, not 1 minute. Thus, like the Stanford Torus, they have to build to a certain diameter and create the smallest habitat able to do that. In practice, you really haven't got much reason to build a torus habitat out past its 2 RPM radius of about 225 meters, let alone beyond the 1 RPM radius, as if you need more living room, you just go for the cylinder habitat or make your donut more flat. Instead of a circular cross-section, you build one more elliptical, or even just a ring with walls and a dome. In this way, you could even have 2 rings touching, and if they're the same diameter, share space through cross tunnels, presumably with airlocks. Or you could rebuild the roofs as a single one, but there's a lot to be said about being able to slam some pressure doors down between 2 separate sections. This means you can keep adding rings as you go, extending the central axis they connect to. Indeed, if you want to, you could make that long central axis eventually curve around into a hoop itself, and on lower gravity objects, like most asteroids, you could build the first donut right over the surface and slowly add more each way, up and down as you mind. Agricultural hoops are also much cheaper. We are pretty sure plants need less gravity to be healthy, allowing you to build the ring longer, and radiation is a much smaller concern. You probably would only need just enough for the structure and soil, which might only need to be a foot or two, or maybe half a meter deep. The same reasoning applies as with populated ones versus cylinder habitats. Land area in a cylinder is cheaper to build, so I generally tend to think the Stanford Torus isn't your city or small nation in space, but your village or modestly large town, port of call, or even a single family dwelling. As we mentioned, the basic design, the one over a mile across, masses 10 megatons, and 98% of that is shielding or dirt and water. Depending on how you lay that out, you've got something like half a square mile, 300-ish acres, or a bit over a square kilometer of land area, or land and lakes. If you're laying that out as a landscape and want hills or deeper lakes, you just insert big hollow bumps or dimples up or down the floor. That would seem like a ridiculous luxury for a single family, and we could build it at a quarter that size for the 2 RPM habitat, major and minor radius each quartered, which would still be almost 40 acres or 15 hectares. But let's consider that bigger version. The asteroid belt alone is barely 1% of our moon's mass, which in turn is barely 1% of Earth's mass, and has enough mass to build 239 billion such habitats. So one per family isn't really pushing it even for that bigger version. We tend to assume pretty good automation and energy abundance when building space habitats anyway, and given the rising desire for bigger homes and lawns, I don't think we should rule out everybody wanting their own 40-acre farm, or 400. There's also way more mass out there to work with, without even talking about disassembling planets or engaging in starlifting. One big moon like ours, or one of the Galileans around Jupiter, could let you build enough for maybe 100 trillion of those 2 RPM donut habitats. I should also note the shielding doesn't have to be rotating itself. You don't really want to be able to see outside space in a habitat that's spinning around every minute or so. As a result, nesting your habitation hoop or drum inside a larger non-rotating superstructure means you can pile bulk matter into that without structural concerns. That's handy if they are some mining outpost that wants an inflatable or telescoping habitation ring they can blow up on arrival, throw a thin shell around, and pile leftovers from their mining operation on. That shell holding up meters-thick regolith and rubble doesn't need to be very strong, given that less than 1% of asteroids have even 1% of Earth's gravity. Smaller ones are way more common, and on most of them, you could personally deadlift the structural mass of a Stanford Torus, assuming you could keep that lift going for potentially hours, given that you still need to overcome that inertial mass. So that might need to be a team effort. Regardless, a thin shell over such a ring need not be very strong to hold up all the shielding it would need on your typical asteroid, comet, or minor moon. Of course, if you cover it over, you can't get any light in, and free sunlight is always nice. We tend to assume the empty middle of the hoop has angled mirrors, allowing you to bounce light in, and only those frequencies or wavelengths you want. You could put a big parabolic mirror out behind one to catch even more sunlight for habitats built in space far from the sun. For one on an asteroid, where that asteroid itself probably spins around every few hours, having some big reflective solar sails and lenses tethered to the asteroid can keep light going to that habitat at the amounts you want when you want them. Giant reflective thin mirrors are also great for power generation and limited station keeping. That only handles photonic radiation, not charged particles, but those mostly come from the sun and aren't going to bounce off a mirror around your shielding into the habitat. I should note that a giant spinning ring with a power supply makes a pretty good magnet for deflecting particles, but in fact it would make more sense to run a power cable out to some electromagnet between you and the particle radiation source. Distance matters more than power when it comes to deflecting particles magnetically. The other thing to keep in mind about space habitats is that it's easy enough to put a bunch of them in about the same place, and even keep them lashed together with tethers for transport, power, and high-speed data transfer. So you could have 100 smaller donut habitats loosely bound to several square kilometers of solar panels, a few dozen dedicated farming habitats, and a variety of space docks, factories, defensive installations, and zero-G environments. You might see this around a lot of points of interest too, or even see a bigger station like O'Neill cylinders with a flock of Stanford Tauri bound to them. Why? Well, as we said, you get more living area out of the cylinder designs, especially when you want big habitats that might be a dozen miles wide and long. The default Island 3 design has 80,000 acres in it, but often you won't have that many people. You need comfortable room for 1,000 employees and their families. One Stanford Torus does the job. One O'Neill cylinder would be rather excessive unless the culture and resources of the time demanded 80 acres a family, which shouldn't even need 1 acre to feed them with modern agricultural tech. The other side of that equation is that if you or I go buy a house on an O'Neill cylinder, same as if we bought one in some suburb here on Earth, we might find we like our home and garden quite a lot, but really dislike our neighbors. Every space habitat is a spaceship. So if a big cylinder habitat decides it's tired of being part of a country or a state, it can move, whereas a county in a US state can't just pick up and leave. Yes, you could in theory threaten to invade or blow them up. Space habitats are not super fragile and are a nightmare to invade, as we discussed elsewhere. But from a diplomatic perspective, it's a lot easier for a country to claim a piece of it can't just up and become some other country, so everybody tends to shrug at succession movements without real and massive tyranny involved. Same for if you decide you don't want to be in a city or township. You can sell your home and move, but the land stays. But a big cylinder habitat of 1 million folks is much heavier to decide to move away and to find a new parking place for them than a more modest tourist habitat. Same, you could build one faster and cheaper, as you could a house compared to an apartment building, either the latter was more economical on a per-person basis. Needless to say, we build both and not just in cities. So I think you'd have way more of the smaller tourist designs than bigger cylinder habitats, though you might have more total people living in the latter, say 10 times more donuts than cans, but the cans hold 20 times as many people. It will also be a lot longer before we not only have 1 million people living in space, but actually have 1 million people needing to live the same place in space, whereas 100 tourist habitats might spread around to 100 different useful areas under development, and more added with time. As we noted earlier, you could have multiple wheels on the same axle touching and sharing a roof for expansion into a cylinder habitat eventually. It may be several centuries before we need even one O'Neill cylinder, while we might already have built thousands of real habitats. In the end, it will come down to how cheap we can build them. It may be the mass needed per person will trump the construction cost as a factor. But for now, millions of available asteroids look like abundant and accessible supplies of building material. I don't think we'll build one of them this century. It's still a lot of space needing thousands of folks living or working in space to justify building some. But we might, and I don't think it'll be too far in the future before we see folks in a Stanford Taurus. So today's episode comes out on Thanksgiving, and that means tomorrow is Black Friday, when all those awesome deals arrive. If you're looking for a good deal that will be great all year round, treat yourself or a loved one to top-notch premium audio earbuds from Raycon. I've been using and recommending their everyday earbuds for several years now, and even my oldest pair are still working great, even though I've accidentally put them in the clothes washer twice. But their newest model takes that quality even further, starting with excellent active noise cancellation for when you're on a flight or try to get work done in a noisy environment. They now feature a 32-hour battery life, quick charging, wireless charging capability, and multi-point connectivity that lets you pair 2 devices at the same time. They are rugged and durable with a beautiful weatherproof case. They stay in your ear, comfortably, instead of slipping out or giving you an earache. They're incredibly stylish, and they're an incredibly low price for premium audio. It's time to save big for Black Friday. Go to buyraycon.com/IsaacArthur today to get up to 30% off site-wide. That's right, you'll get up to 30% off everything on Raycon's website when you go to buyraycon.com/IsaacArthur. We'll be taking a deep dive look at other space habitats over the winter and spring, like the Bernosphere, but part of engineering space habitats is remembering they aren't space stations meant just for humans, but whole functional ecologies. So we'll start December off by looking at how we can be building biospheres on new planets and inside space habitats. After that, we'll look at the Medusa Drive, a spaceship design that uses nukes to pull a ship forward. Then we'll ask how technology might permit more off-the-grid living in the future. If you'd like to get alerts when those and other episodes come out, make sure to hit the like, subscribe, and notification buttons. You can also help support the show by becoming a member here on YouTube or at Patreon, or check out other ways to help at isaacarthur.net. Until next time, thanks for watching, and have a great week.